Wow. So that's quite a diagram, huh? That's one of those kinds where you can put up in a classroom and you can put everybody to sleep almost immediately. And I don't want you to go to sleep. So what I'm going to do is simplify this a little bit for starters. If you just look off to the upper left, you have a more simple model of scientific inquiry. And very often we start at the bottom of those three words there. There's the prediction, explanation, and observation. And a lot of times in the early phases of science in a particular field, we see observation really playing the dominant role. It's just knowing what's there. So, for example, um, if you go back into, say, 16, 1700s, we finally were able to observe enough of the Earth's surface, the continents, the oceans, and so on, to get a sense that amazingly the coastlines of Africa and South America, and for that matter, really the Americas overall, and Europe and Africa, look like they could have fit together sometime in the past. That's an observation, but it's not really scientific, but it's a good start, right? Eventually we learned that in fact they had fit together, and that's a whole story for later in the term. And if you've studied plate tectonics, continental drift, you probably know that story more or less, starting with Sir Francis Bacon. But what happens eventually in science is that we have to go beyond saying, gee, those continents looked like could have fit together, and even pointing out, for example, that the stratigraphy, the different layers, for example, of sediments, of the geology, of the fossil record, and all of that, show a nice match between how Africa, for example, and South America would have fitted together. Um, so we still have those observations then, very powerful observations, not just that the continents fit, but then the fact that if you look at carefully at the details of where they fit together, it matches perfectly. But still, the problem is, how do you explain that? How could you explain that thousands of miles of ocean basin separate these supposedly once joined continents? That seems kind of ludicrous. We need some kind of an explanation, a plausible causal mechanism within which those continents could have been split apart and pushed away from each other when in fact once they would have been a common landmass. And so eventually that's what happened with plate tectonic theory. And if we look at it now, we're actually able to even make some predictions because we understand more about the mechanisms that cause the continents to move around. The prediction part happens. But very often, all along the pathway from observation, explanation to prediction, we run into all kinds of problems and we have to rethink. We have to go back and collect more data, refine our explanations of what we think is happening. In other words, what causes this to happen? And if we don't get it right, we have to come back again. And so much of what's going on in that blue box on the right there is all really about that. But by and large, it boils down to observation, explanation, and prediction. And so another example of that that's kind of fun is the whole story of carbon dioxide in the atmosphere. If you look at that link there, and presumably you already saw that when you're going through the notes, but if not, you want to go back to the PowerPoint and look at that HTTP, HTTPS link there uh, from Fourier to Arrhenius. And that's a great story. 200 years ago, 1820, Fourier uh, observed that the Earth should be much colder than it is. He looked at the basic amount of energy coming in from the sun, and he looked at the temperature of the Earth, and he said, it doesn't make sense. Unless there's something going on in the atmosphere that's trapping a lot of that heat that comes off the Earth, it should be much, much colder than it is. And eventually, John Tyndall, the Brit, by the 1860s, had looked at that question a little more. They were talking about carbon dioxide, or they call it um, carbonic acid in those days, but carbon dioxide. And then by, say, 20 years later, there was even more work on this. Arrhenius, the Swedish scientist, actually started modeling what the role of carbon dioxide actually is in the atmosphere. And he even came up with a prediction that if we were to double it by combusting more coal, that was the main fossil fuel in those days that put carbon dioxide in the atmosphere. If we doubled the atmospheric level of carbon dioxide, that we would end up with a much warmer Earth, maybe upwards of 6 degrees. And so there was an early prediction of this. So it was pretty well understood even in the 1800s. Yes, carbon dioxide's there, And yes, it absorbs heat. And when you have more carbon dioxide, you have more heat. And consequently, also, we've had done plenty of laboratory experiments. In fact, there's some common experiments you can do in science labs. Some universities have these, even some high schools show putting more carbon dioxide in a chamber absorbs more heat. And so this isn't mysterious. So we've known a long, long time of that relationship. Only recently has been this somehow become somewhat controversial. But if you just look at the physics of it, it's really straightforward. So at the basic level. So that's just a quick look at this whole question of how observation, explanation, prediction work. What I've described with the carbon dioxide story is the explanation of how the atmosphere is warmer than the physics would already suggest. Without the greenhouse gases there, it wouldn't happen. The prediction part, of course, is that's where we are now. Is if we keep putting more of it in there, we're going to make the atmosphere warmer and warmer and put in motion some other physical processes, some of which will be problematic, and we're going to look at that.